Okay, in this lecture we're going to continue on from our starting point, which had been, well, all the way back to the beginning. We had looked at an RC and an RL, and then we looked at, lastly, or most recently, an LC response. All right, so we want to continue from here to now looking at the full-blown monster, if you will, of an L, an R, and a C. And last time we ground through the math and end up finding quite an elegant solution. And what we want to do now, before we grind through the math on this one, let's just look qualitatively at what we might expect. Okay, we're engineers after all. We want to harness the usefulness of math, but we don't want it. We don't want to be at its beckon, I guess. We want to think critically about how we think a system should respond before we just blindly turn the math crank, because after all we might make a mistake along the way, and we want to know whether there is a mistake or not. It doesn't make sense with what we understand intuitively. So let's consider several cases of an RLC circuit. So let's first consider the case where R is 0. That was what we did last time. We also had initial conditions of IL and VC of 0. And here's the response that we had in time. We had a steady state response of Vs, and it started at 0. This is Vc that I'm plotting, and it went up and up and down forever. All right, it had the form of Vc of t is equal to Vs times 1 minus cosine omega n t, where omega n we'd found as being 1 over the square root of LC. So it's the oscillation frequency is dependent only on the values of L and C. All right, now let's consider the case where R would be equal to something small. And I put it in quotes because we have no idea what small is at this point. But we'll go ahead and at least we can anticipate how it would respond. And, all right, steady state value is Vs. And now let's just think about this. An L and a C are like a mass and a spring mechanically, right? And if you throw in some dampening, some viscous dampening, some drag, some viscous dampening, and you set off that spring mass to oscillate, you expect that in time it will cease to oscillate. It will decay. And so I'm going to just assume here, or postulate, I guess, that I'm going to oscillate again at, I guess, roughly the same frequency, but it's going to decay. Okay, it's going to decay. Now let's consider a case where we now have R is bigger, okay, just bigger than the smaller value. Again, the same initial condition, Vc and IL equal to 0. Let's see what we might have here. I'm going to just claim that we would have a more aggressive decay, and so it'll look like something like that. And what might this envelope look like? Well, we've seen that before in first order systems. An exponential decay would fit this nicely. Now we have no idea if this is what the solution actually is, but we're just trying to get do a little prediction on how we think the system might respond before we dive in and grind through the math. All right, so if that is the solution, or the way that this system responds when you add a resistor, then let's return to the complete response and consider how we might capture that in our expression. So we had before, with no resistance, we had, this is the case for VC of 0 is equal to 0 and IL of 0 is equal to 0. We had VC of t is equal to Vs 1 minus cosine omega nt. Right? Now, with some resistance, same initial conditions, same ICs, we could capture that exponential decay as follows. We could still have the same steady state response, right? That is not decaying exponentially, right, like the transient response. So we still have Vs, but now we're going to have Vs times cosine omega nt, and we're going to multiply that by this exponential e to the minus t over tau. And that functional form there will indeed be able to predict something like this. Right? That's very reasonable. And what we'll have, if we split this complete solution into two parts, we'll have a particular response, and we will have a homogeneous response, which will go like this, right? Homogeneous or transient. All right. So now we have an idea of what we're going to look for when we grind through the math. We have yet to show that that's actually the case. So we'll take this in consideration as we actually solve the differential equations for the RLC circuit.